Good afternoon, everyone. My name is Claude Gus, and welcome to my talk on radio propagation modeling for 5G and beyond. I would like to thank the EuCAP 2021 organizer for this very nice invitation. And before entering directly into the talk, I would also like to thank all the PhD students in my team, postdocs and visitors, as well as many researchers from various cost actions, 2100, IC1004, and CA15014, which is also known as IRACON. My talk is about 5G, 5G plus, as well as beyond 5G radio channel modeling. So we know that these communication will go beyond the traditional cellular communication between the base stations and users. In particular, with two aspects. The first one is the massive IoT machine type communication aspect, which means that we will also be dealing with industrial environments as well as body-centric scenario. And the second corner of this well-known triangle is indeed the fact that we do have low latency applications such as vehicular networks for autonomous driving, as well as industrial automation. So these two new requirements, new types of environments also call for new challenges. And in particular, if we want to reach higher data rates for cellular communication as well as for other applications, we would require higher bandwidth, which means that one possible solution is to move to a millimeter wave, as well as going into frequency reuse. Frequency reuse meaning that we need to implement some interference management technique or use massive antenna array, also known as massive MIMO. Regarding the reduced latency and the energy challenges, we might need to use an optimized localization for the computing, which will imply the use of cloud and fog radio access network, as well as for mobile edge computing. I will not talk about these aspects here in my talk, but will more focus on the aspects which have an impact on the way we do channel models. So what are the questions I would like to talk about today? The first one is about well, a bit of a myth that might not actually be true. We know that really fading has been used for many years as the worst case scenario, but is it actually the worst case scenario is an interesting question, which I will talk about. Then I will also talk about stationarity, in particular when we deal with vehicular networks. What is actually stationarity? The third point will be a comparison between deterministic and stochastic approach, and actually how can we merge them? Can we make bridges between these various models? The fourth point will deal with millimeter waves, in particular the multipath richness and the surface roughness that we meet at such wavelength. Then I will talk briefly about the reference channel models that were built within the long history of cost actions, the latest being IRACON action, which I was happy to chair. And finally, a few words about some emerging technologies and application before going into the conclusion. So the first point is about fading. And when we look into machine-to-machine fading, we see that we do have in IoT industrial scenario highly reverberating environments, which means that we do have very high multipath richness, which might make the case for actually the really fading, which has been traditionally used for cellular communication. And here are some measurements taken from NIST, and we see indeed that we do have fading which is reminiscent of really fading. Is it actually really fading? It really depends on the type of scenario that we deal. And here is an experimental setup that we had at UC Louvain. So we used channel sounder at 3.5 gigahertz. And instead of using the MIMO channel sounder as a traditional way, we use this MIMO sounder by using very long cables going from the sounder and distributing antenna in the various surfaces of a corridor. Okay, so all these cables lead to various surfaces, And at the end of each cable, you do have a small antenna, a small dipole antenna. And we used this dipole in different setup, either where the antenna were really attached to the office and fully static, but they were moving on both sides of the link, so both at the transmitter and at the receiver. And so we measured the channel from room to room and room to corridor for different mobility scenario. So this is an example of a scenario. So you do have some transmit antenna which are distributed, for example, in this office, and so on. And then you do have receive antenna here on this office. And so you see that you have different walls. Some are bricks, some are plasterboard. The goal was to look into the channel between these different nodes. And this is a typical antenna that was installed on one office. So this is in a typically fixed setup. But then sometimes the antenna were just moved by some human user. And so this is exactly what we measured. We measured that the worst case scenario was actually not really fading. What we did observe was that in this worst case scenario, we had as well double Rayleigh fading, so which is much worse than Rayleigh fading. And when did we see double Rayleigh? Actually, when we had this type of scenario, we had actually room-to-room transmission, but because the walls were quite thick brick walls, the main transmission path was along the corridor via waveguiding. And when both antenna on transmit and receive side were moving, we did observe actually double Rayleigh fading. Now, to integrate this double Rayleigh fading in a more general models, we built an hybrid distribution, which we called second order stochastic fading. So it's SOSF in short, which in which the channel is consists of three main contribution: a constant dominant contribution, which is the same as the one which we use for Rayleigh fading, a Rayleigh distribution, so a single Gaussian, and a double Gaussian, double Rayleigh fading, W0, W1, and W2 being the weights of the different contribution. Of course, we can reduce these weights to 2 if we normalize the fading to a unit energy, meaning that we do have actually two weights, alpha and beta, alpha being the weight of the double Rayleigh fading and beta being the weight of the dominant constant path. So beta is a bit similar to the Rayleigh k-factor, although the k-factor will only be W0 squared divided by the sum of the other two. Okay. And so we can measure the variation of alpha and beta as a function of the time as we move. And you see here that alpha and beta do vary quite significantly over time, meaning that the channel is non-stationary. And we do see that we do actually have a very high alpha value in some region, in some temporal region, high alpha, meaning that we do really have, in this case, pure double Rayleigh fading during this period. Beta is equal to 0. We don't have any constant path, and we do have a mix of Rayleigh and double Rayleigh, sometimes purely double Rayleigh, during some time interval. Okay, so Rayleigh fading in machine-to-machine, peer-to-peer scenario is actually not the worst case. When we do have double mobility, we do have double Rayleigh fading as well. And when we mix all these contribution, we can build actually an analytical formula for this SOSF fading, although it's still not a fully closed form since we still do have an integral here. But my point here is that in large part of the time interval, we do have double Rayleigh fading as well when we have double mobility, which is often met in machine type communication, IoT networks, or peer-to-peer type of configurations. Now, the second part I wanted to talk about is indeed the stationarity. We have seen here on this slide that the fading parameters do vary over time. So we do not have a full stationarity over a very long interval. This is even more so in vehicular networks. So when we do have an experimental data from vehicle to vehicle transmission, so we had here two vehicles moving along the road. And if we look into the time varying impulse response, we do see that here we do have paths appearing okay, which then disappear, which translate actually into a variation of the delay spread as illustrated on the graph below, when we have the calculation of delay spread. And you see here in this region, we do have a very high delay spread, more than 100 nanoseconds, meaning that the channel might not be actually stationary. Now, which brings me to the question, what is actually the stationarity of the channel? If we look into a very mathematical definition, we might end up in some very tricky situation where we might not be able to fully characterize the stationarity. That's why in propagation, we have used the definition of, because it's convenient, quasi-stationarity. What does it mean? It means actually that we say that the channel is quasi-stationary when the multipath structure remains sufficiently similar, both in delay and in angle. Okay, it's not strictly stationarity, but it's close enough, and it's actually very practical because we can then measure it. The question is, when we want to measure this quasi-stationarity, what is the impact of the measurement system, of the measurement setup, actually? If we had an infinite bandwidth, if we had an infinite number of antenna, and so an infinite resolution in angles, we might reach what I call the propagation level stationarity. So this is a very theoretical definition of stationarity, which would be measured if we had an infinite angular and delay resolution. In practice, we do have a finite bandwidth, we do have a finite size for the antenna array, finite aperture, which means that we do have quasi-stationarity interval, which are measured with a worse resolution, leading to longer interval actually that what would be measured at propagation level, meaning that if we increase the bandwidth beyond the measurement bandwidth, the stationarity will actually be decreased. Let me illustrate this by a graph. So this is the stationarity distance, because we translated the stationarity time using the speed of the vehicles into a distance. Okay, and we see that we increase the resolution of the antenna array that was used to extract the stationarity interval using the correlation matrix. Well, we do have a decrease of the stationarity distance, which can be quite significant. If you look at the median here, we do have a stationarity distance which goes from around 50 meters to less than to around 10 meters. So we divide by 5 the stationarity distance just by decreasing increasing the resolution of my antenna array, going from a few antenna to more antenna. Now, this is important because what the system will see is, of course, the stationarity that is parameterized by the system parameters, meaning the number of antenna that we use on the array, the number of tap that we use in the impulse response, so the bandwidth of the system. And so it's very important to know that actually the stationarity that we measure might not be the same as the one that we meet in a given system using the real number of antenna, the real bandwidth. And so we need to be very careful about the conclusions that we draw about the stationarity when we do use a resolution which is poorer than the one that will be used by an actual system. Based on this measurement, we actually built a non-stationary vehicular channel models that was done jointly with Beijing Jiaotong University. And we do have transition between one stationarity region to another via a birth, survival, and death process for the multipath component. And you see here a comparison between the simulation here on this column and the measured channel impulse response in that column. And we do see that, of course, they do not match perfectly because the goal is to reproduce the stochastic behavior of the channel. But when we look at the distribution of delay spread and angular spread over time, over different stationarity region, we do have actually a very good agreement. Okay, now the third point I want to address today is about the deterministic versus the stochastic aspect of models. We have been using the deterministic aspect for a long time, but with the gain of computing power, ray tracing models have really attracted a lot of interest in the last 5-10 years. And they've also been including a model for the rough surface. The rough surface scattering is actually not about the microscopic roughness of the brick, for example, but really macroscopic irregularities resulting from the use of balcony, windows frame, doors, irregularities along a building surface. And this was modeled using the well-known model of Vittorio degli Esposti, known as the effective scattering roughness. Now, this model has been implemented in ray tracing, where we divide an homogeneous surface of facade into tiles, each tile being characterized by a random scattering, okay, using an inversion, for example, scattering model for each of the tiles. Now, the question we wanted to address is actually when we deal with measured channels and we build models from measurements, we do have a measured impulse response using an high order estimation algorithm such as SAGE or RIMAX. We do have an extraction of specular components, okay, and this is the red curve. But when we compare the measured channel impulse response power delay profile in blue and the extracted specular components, we do have a huge difference, the difference being illustrated in green. And we see that this green curve looks more like a continuous multipath, which is exponentially decreasing over delay. This has been modeled in measurement-based channel models by the concept of dense multipath. So it's a continuum of paths which are modeled stochastically. And the question we wanted to deal with was, is this the same as the diffuse multipath that we model in ray tracing? This is, of course, very hard to compare. But what we did was to conduct measurements in a room, which we then modeled using ray tracing and using a diffuse multipath model for the macroscopic roughness. And so what we did was to compare the angular spread for both the measured dense multipath and the simulated diffuse multipath. And we do see here in this graph that we do have a good agreement in the sense that the angular spreads seem to match for a number of measurement locations, which tend to indicate that this dense multipath is not only a measurement artifact, but it's actually also something that has some physical reality and can be therefore modeled using also ray tracing. Now, another aspect of the deterministic versus stochastic model is that we do have more and more in ray tracing random objects appearing because they are moving. We also have objects with very funny shapes, such as cars, such as a lamppost, and so on. And the way to model them into ray tracing might not be easy, as these shapes do not fit sometimes very well the ray tracing formalism, which is more about buildings and parallelepipedic blocks. So how do we deal with that? Well, what we try to do is to build some hybrid model where, for example, we model a plane, because the goal in this project, which was conducted at UC Louvain with my electromagnetic team colleagues, was to model a plane. We wanted to model an airport, to model a plane using a method of moments, and then to plug the plane into a model of the airport, which was built using ray tracing. And so how can we merge, how can we hybridize the model of a very detailed model of the scattering by the plane into the ray tracing? This is some topic that we are still working with. So how to represent complex shape objects into a ray tracing, and how can we smoothly merge them into a single simulation, keeping the computation time limited. Of course, this means that we will build a library of objects and then plug them into the ray tracing. Okay, going to the next aspect is millimeter waves. We know that millimeter waves will be used by 5G and 6G, certainly for backhaul. For access is a bit less clear because we have a lot of challenges dealing with millimeter wave access, in particular the antenna directivity. What are the multipaths that we are actually dealing with, the impact of the hand of the user. The tropospheric effect might not necessarily be significant, even though in tropical regions they might have some impact. And This means that millimeter wave have to be modeled either using ray tracing that was done at various research institutes, in particular at UC Louvain, and I will present you some results of ray tracing at millimeter wave and a comparison with measurements. Also using experimental data at various institutions, New York, Ilmenau, Durham, and within Costa Rica, to model the diffuse scattering, the multipass richness, and the clusters. Okay, so there is a ray tracing experiment that we did at a comparison between ray tracing and experiment that we did at UC Louvain. We used two frequencies, 12.5 and 30, using a mobile transmitter at street level, which was a circular horn with vertical polarization. At the top of a high building, we put a static receiver, which was using a correlated horn, also with vertical polarization. We were at each measurement position aligning the antenna beam with the line of sight, and we measured along 60 meters in two periods of the year, in summer, where the trees were in full bloom, and in winter. And that particular winter, not only of course, the leaves were not present, but also all the branches had been cut because the trees had been trimmed before winter. So we had actually no branches on the trees. This is the environment. So you do have here the street as seen from this green arrow. So this is what you see when you position yourself here and looking into the green directions. This is what you see here if you look into the red direction. So you have here the street. You have trees here, which are represented here. These are these trees. We also had trees further down. And so the transmitter was moving down the street. And this is the comparison between the measurements and the ray tracing simulation. We do see that the matching is quite good. So the measurements are the plus and circles. The ray tracing results are the plane curves. This is at 12, this is 30 gigahertz. And here we do have in blue the winter situation and in red the summer situation. We see that when we do have trees, we do have a huge attenuation by the trees around 15 dBs at both frequencies. We also do see that the fading is quite limited, at least from the ray tracing perspective, because we here see a more like sinusoidal behavior at both frequencies, which means that we basically have two rays, right, interfering with one another, meaning that the multipass richness might be very limited at millimeter wave. Okay. Now, another questions we might deal with is the scattering at millimeter wave. We have the idea that the surfaces might get rougher at millimeter wave frequencies. Is it true? Actually, if we look at the basic Kirchhoff approximation and we look at the scattering cross section, you might see that it might actually be limited. So the main challenge might not be the scattering. The main challenge might be that basically when we look at building at millimeter waves, well, your wave might be reflected either by brick or by windows or by trees. And this might change quite rapidly as you move, as the specular points move along the facade. So you might have somehow not necessarily roughness, which will create some stochastic behavior, but more like a rapid change of type of surface as you move along the street. Finally, about the clusters at millimeter wave, what is the richness that have been reported? Well, we see here in an experiment by New York University that the number of subpass per cluster was most of the time equal to 1. Now, what is the meaning of a cluster containing only one pass? Well, it means that we might have a very deterministic behavior, and this goes along the observation here that we do not have significant multipass at millimeter waves. Of course, when we include the antenna pattern, which means that the antenna pattern must absolutely be accounted for, and this implies that the GPP model for millimeter waves might actually be quite far from what we measure in reality. Now, talking about 3GPP models and reference channel in general, there were two main models developed in the past, Winner 2, which was then extended by Quadriga, and that's basically are based on 2GPP models, and then cost models, COS2100 and its extension made by IC1004 and IRACON. Both models are the same. In essence, they are geometry-based stochastic models. They do have some differences in the way they model channel dynamics. They were extended for multi-link capabilities, and then more recently, Metis project produced three new models. One which is more winner-like, cost-like if you want. One which is map-based to account for urban geometries, and one which is more of an hybrid. I will here deal with the cost model because these are the models that were developed by Actions, which have a long history of developing models. The last one being IRACON. So how do we parameterize the model? We do measurements by preparing the measurements, then we do channel sounding. We then have a parameter estimation. Then we cluster our specular path into the angle and delay domain. And finally, we do have the validation, the development and the validation of the model. So the model are geometry based and deal with a double directional model. So we do have paths which are characterized by their angle of arrival, angle of departure, and delay. And this is modeled into then a separation between the channel, including the polarization aspects, and then the antenna array, which are used. And of course, this is both what we measured and what we model. So the goal being, of course, to reproduce the channel. And then we use that to build an imaginary map for the radio wave scatterers, which are then grouped into clusters for stochastic models. Now, how do we do that? Well, we use a parametric model and we try to match our measurement with a model of the different paths. So we try to optimize the number of paths and the delay, angle of departure, angle of arrival of the different paths. When we do this, we find the number of points in the delay angular domain. So here this is for just one angle of the angle on one side. So where we do then build some clustering of the different scatterers. By the way, we have been doing this for many years already in the whole propagation community. And so this is actually already machine learning and artificial intelligence. So this has been used for quite some time already when we build models. Now, when we have the clusters, we can then model the cluster's properties, like the spread in delay, the spread in angle, and the mean direction, mean delay, so that we can then build our imaginary map. So all the cluster here, okay, and then we build a model. Finally, I've been talking about specular paths, but we do also have the rest. So the dense multipath, which I talked about earlier, which then can be used to improve the prediction of the model. And the dense multipaths are actually modeled by extending actually the specular multipath, so into the angular and delay domain. So we do have here a dense multipath appearing around my specular path. Now, how do we build the model? Well, the COS2100 model is based on a visibility region, so where we assign to each cluster a visibility region, and when the mobile receiver is in that region, we do have a visible link between the transmitter and the receiver going through that cluster. Okay. Now, the model has been extended to include a multi-link scenario. When we look into measurements from multi-link, we do find that actually a number of paths, when we do have here two base stations, a number of paths reaching the receiver are actually common for the two base stations. And so we wanted to model the commonality, the similarity between the paths between the different base stations. You see here that you can reach a very high percentage of similarity between the paths reaching the mobile when paths are originating two different base stations. And so to model this, we define what we call common clusters. So clusters being common to the channel seen from base station 1 and base station 2. I will not go more into the details about that. We also extended the model to massive MIMO using again the concept of visibility region for subarrays. So within my massive MIMO arrays, I divide it into subarrays, which correspond to different visited region. I really invite you to use the cost model, which is freely available on a GitHub here, and so to use it for your simulation. Of course, it's very nice because it allows dynamic channel simulation. It's scalable for multi-link and massive MIMO extension. The small drawback of the model is that it's still lacking scenario model parameters for some scenario, in particular outdoor to indoor scenario, but you are really invited to contribute to this model using the open access that we have provided. Now, finally, a few words about emerging application. I would like to talk about multi-everything networks, in particular using waves for more than just communication. We know that we can use antennas for radars, for localization, but also to transmit power. And so a new paradigm which has emerged is the joint information and power transfer. And of course, when we try to model this, so we will need to model the energy harvester within my receiver. And the way we represent the diodes, we're moving a bit away from the model of EM waves, but we need to represent as well the receiver. And the way we do this model will have an impact on the harvested power. So these are slides taken from a colleague from Imperial College, which has been dealing with this aspect. Now, if I want to conclude, beyond 5G models should actually reinforce the modeling of single channel properties, especially polarization is still often overlooked, also when we do measurements. And it's useless to do modeling of polarization when our measurement does not include a way to model this polarization effect. We have to deal with stationarity, dual mobility, and these aspects must be included in the model. We need to support multi-user, multi-link, multi-application scenario, including new emerging applications. We need to be frequency agile and somehow consistent over all frequency bands. This is like the holy grail, right? To have a model which would be valid over many frequency bands, but this is something that is still missing. We still have big holes between 6 and 60 gigahertz. And at the end, we need to be physics-based and validated by measurements. As someone was saying very rightfully, everyone believes in measurements except those who made them, but no one believes in simulation except those who made them. Now, this concludes my talk. I would like to thank you very much for your attention, and I would be happy to answer any questions you might have.